Hi, this is Farhan, and I'm going to be presenting reducing the effects of radiation damage in cryo-EM at liquid helium temperatures. So this paper came out quite recently in February, I think, and it's very relevant for anybody who's trying to do cryo-EM. So the reason we do cryo-EM is to study beam-sensitive materials like proteins and DNAs. So we cool it down to liquid nitrogen temperatures, and we try to image them. So we can obviously cool it down further and reduce the damage further, right? 5 to 10 times more if we do it at liquid helium temperatures. But the problem is we cannot see any improvement in the resolution. So the group of researchers from University of Massachusetts Medical School and Professor Christopher J. Russo and group, they have tried to understand what is really going on and why are we losing this resolution and what we can do about it. How can we mitigate this, right? So as you can see here from this little graph here, and I'll show this later on, the resolution doesn't really improve between these two temperatures, especially at this curve right here. So this is what we're trying to address. So what the researchers I have identified, the main reason we are having these issues is because of the movement of the specimen. So let's take a look at how a cryo specimen is made. So this is a grid right here with all the holes here, and then we have frozen water, which is amorphous, and that is carrying our sample. It could be protein or anything. Here they've studied it with gold nanoparticles suspended in it. And so there are many parameters that would affect the measurement. Obviously, the thickness of this film, the thickness of the frozen water film, the distance between here, and also the temperature. So as you can see, for 81 temperature, it's more or less fine. But as we cool it down, there's more strain being developed in the grid itself, and that is imparting the strain in the water. And you can see that the sample's moving, and then after electron radiation, it is already it buckles and it forms this kind of a arched way, and then we can see this in videos they've taken. Here you can see this happening 0 degree tilt axis, and this is 30 degree tilt axis, and they can actually analyze this to show that this is happening perpendicular to this tilt axis itself, and that's why they have shown us that illustration before. So there are other things that also affect it. One thing would be how thick the foil is. Obviously, that would control how much the thickness would be for the frozen water. So if you have thicker foil, you get more displacement and you lose more resolution. Same thing with beam diameter. Of course, the fluence and the bigger the diameter of your electron beam would impart more energy, and that would cause more buckling. That would cause yeah, more buckling and will more displacement, per se. So this was quite well known of like why this happens. So the one thing that people have already assumed is that okay, we have this frozen water and we're cooling it down further, and so maybe because of strain and cooling, it actually changes density. It goes to a higher density phase. Right, because there's also proof, like, okay, the diffraction pattern changes from 3.7 Armstrong to 3.2 right here. So you can see this little band here that will change with fluence, and then goes slightly bigger, so it becomes smaller. And so but if it is actually doing a phase change, we should see it in that means if the density is actually changing. If the density is changing, the electron density is also changing. That means we should be seeing a shift in the plasmon signal of water, which is they've recorded here. As you can see that there is no shift in those two things. So density is not actually changing. Something else is happening. Something else is going on. So we can exclude the possibility that density change occurs. There are other effects. The one effect that these researchers have, kind of branded as like why this is happening is because radiolytic fragmentation of amorphous water. So this is an extreme case here for both temperatures. As you can see, we have all this bubbling. That means hydrogen is bubbling off the water as we irradiate it at different temperatures. As you can see here, at 13K, there are more bubbles nucleating per area compared to 81K, and this is an extreme case at very high fluence, so you can observe this. But usually in normal case at 81K this happens, and the hydrogen escapes, or it calms down, it recombines, or there are many cascades of events that are happening, and what essentially would happen is that it will calm down and you can still image them. But at 13K that does not happen. That's phase 3 combined, and that's why we're having we'll have this issue. So we can see this happen in biological samples. This is a sample of viruses, and you can see there's uh, lower amount of bubbling happening here, but there's more happening here at the interface of these samples. Um, so at the same time, so now we understand that the foil is imparting strain on the frozen water, and that frozen water will expand to buckle and release strain, and then this also, like, the strain is also causing giving it motivation to bubble up, and obviously they've you can see from this they've recorded the motion of these particles, and it does buckle perpendicular to the tilt axis, which is like, if this is the tilt axis, this is what they're where they're going. That means that it's buckling up, it's actually expanding or doing something. Because we cannot change the property of water, which would be the Young's modulus of water, at that kind of a solid phase, we can change the film thickness, and we can also change the diameter of the suspended frozen waters. And this is what the researchers ended up doing. They figured out that if you change the aspect ratio of your grid, more than 5:1, so your flat part would be quite big and compared to the whole. So this obviously, you lose a lot of imaging capabilities from the sample, but you can actually gain resolution, and you can stop this kind of displacement that's happening in the sample, and you can definitely you can see that from here as well. So this is the displacement, and for 81K you can see that, okay, for 300 nanometers, 100 nanometers, the displacement is quite the same. It becomes quite big if it goes to a micron level, but for 13K, if this is 300 nanometers, displacement is quite high. So what they've ended up doing, they've produced 100 nanometer holes in a gold grid, and effectively the displacement kind of goes away. So how can we quantify this improvement in the resolution? What they've done here is they've compared 300 nanometer grid holes versus 100 nanometer grid holes, and they've used B factor decay fitting, which is this, and we'll get to that. So the main thing is they've done Fourier shell correlation for both cases, and you can see for 81K and 13K, the resolution doesn't really improve in the normal case. But once you've changed the hole size into a smaller diameter, you can see this improvement happen from the whole range, and you can see the 13K having high resolution from this metric. Second thing, you can see the relative amplitude of your signal versus your fluence and resolution. You can see that for this case, you have these two black bands in 13K, which is limiting your ability to get high resolution and good signal noise ratio at high resolution. But for this case, you can see that no, that we don't see that anymore. It's far more improved. Even at lower fluence, you can have quite a high resolution with really high relative amplitude. And at the same time, if you compare the B factor decay here and here, you can kind of see that, okay, we have this non-linear part here, and then you have the linear decay, which should be linear decay. And obviously 13K has a slower damage compared to 81K. So we can see that, but for 100 nanometer grid holes, you can see that even this asymmetric part has, or like a nonlinear part, has become quite linear for 13K, and the slope has also improved to a point where you can definitely see that there's less damage here compared to the 81K. So they've provided this data set where they've done quite a bit of statistics, and they're showing is that for epoferritin structures, they've seen similar improvements in both cases. You've seen they've seen at least 1.5 times to improvement, like mostly 1.5 times improvement, or like a 1.3 times improvement here, 1.5 times improvement here for different for these samples. At the same time, so they've constructed this graph for us to kind of understand the whole picture here. So you have a lot of these different effects that that's happening apart from the radiation damage, like pseudo Brownian motion, charge fluctuation. So they've taken all that into account and they've normalized that. And then after that, you have your radiation damage. That's obviously with fluence. You're losing your beta factor, like how much information retention you're having. And so they've shown that for radiation damage at 13K is about this line, and radiation damage at 81K is about this line, and this is the raw data they're showing. So as you can see, this is at 100 nanometers. And for each of the nanometers, if you keep increasing your diameter size at 300, you have this, and then you have 2 micron at this, so you have this nonlinear part that's happening just because of that. And so main point being, by engineering a grid that and understanding the effects of how radiation is affecting the specimen itself, and engineering a grid that would mitigate that effect, you can improve this resolution at lower temperatures at 13K. So you're not only preserving your samples, you're also improving the resolution to at least 1.5 times in terms of like the total thing, the complete thing. So why is this important? So this work provides a greater understanding of the multitude of factors that are at play during cryo-EM measurements. Liquid helium temperatures are 5 to 10 times better at mitigating radiation damage, but with the accounting for all the effects, we get after we engineer the thing, we get 1.5 times improvement. But there was a lack of systematic understanding that plagued the use of this temperature range in measuring beam center sample. But now we found a bit of a solution. We have developed a better understanding through this work. And so this provides an effective solution to imaging at liquid helium temperatures, obviously, that we've discussed that. And then this also provides guidelines to statistically benchmark the resolution as a function of fluence and as a function of different other things. So that being said, I think this is a very good paper, a very good technical paper, and this actually provides a lot of inspiration for how we can mitigate damage for other non-biological beam sensitive samples, and we can kind of start probing different areas of the effects that we might start to understand how to image them better if we kind of take this as an inspiration. So that would be it. Thank you so much.